One next speaker is Vincent Tassion, and he will tell us about phase transition of Boolean percolation.
Okay. Yeah, thank you very much. So I apologize for the change of title. So I will discuss the phase transition of Boolean percolation. So this talk is about a paper which is belong to a series of papers investigating the phase transition for percolation models with dependencies. So initially, the first thing to look at is Bernoulli percolation. So you look at Bernoulli percolation in ZD, and it's known from Eisenman, Barsky, and Menchikov that you have a sharp phase transition. Below a critical point, you have exponential decay of connection probabilities, and above you have long range connection, like you have an infinite cluster. And this is expected to happen for a very large family of models, but the original proof was using some properties which were very specific to Bernoulli percolation. And using tools from Boolean functions and a randomized algorithm, together with Hugo Duminil-Copin and Aran Haufi, we managed to prove sharpness for a model with dependencies. So included FK percolations and also Voronoi percolation. Today's talk is based on a Boolean, will be related to Boolean percolation, where we also prove sharpness, but in this case it manifests in a kind of a different way, that we don't have all the time exponential decay in the subcritical regime. So this I will not really detail the technique to prove sharpness, because this is more technical here and it's not the best way we see the argument, but I will more insist on the specificity of this model. So let's first start with the definition. I already lost my red chalk. Ah no. So maybe I put here the definition. So we are working in dimension d larger than 2. We fix the parameter lambda, which is just a positive number, real number. And we consider mu, which is a probability measure on R plus. So the model is constructed in, the process is constructed in 2 steps. So, first step, we consider a Poisson point process of intensity lambda in Rd. So here I just draw in a small box, so you have some points, so on. And step 2, so let me denote it by eta. So step 2, so for every x in eta, so every point, I draw a ball of some random radius, Rx, which, with respect to this low mu. So I look at every point, and around every point I draw a red ball. So this is x, and this is Rx, and these radius are random. So let's say this is something, this looks like something like that. Maybe they overlap. Okay, it's clear? And we are just interested in the set O, which is a random set, which is just the set of occupied points. It's just the union of all x in eta of the ball and the Euclidean ball, center x and Rx. So they are just the occupied point. When I say occupied, I mean this point, which are color or the red point. And the vacant point, they are just this is just the complement of O. So just to fix the notation equivalently and more formally, and it's actually very to do computation. It's actually it's much nicer to think a bit differently. It's just we consider omega, which is just a Poisson point process on Rd times R plus with intensity lambda Lebesgue times mu, and define O to be just the occupied point is just the set of x R in omega ball x R. So maybe this is easier to see as a definition, but this is easier to do computation. And we just write P lambda, so formally P lambda for us would be just the law of omega. Okay. Are there questions so far? It's clear? Okay. So first question, so I will ask a question. Is it trivial? So the first question is that, do we color everything or not already? And this, it will already give us some non-trivial condition. So if I look at the number of balls that covering 0, this number of balls is just a Poisson variable. It's a Poisson variable with intensity with a parameter which is just Lebesgue. So if there is a lambda, I don't care so much about the constant, times mu times the set of x R such that x is smaller than R. And this is this is just exactly of the same order as the integral from R equals 0 to infinity up to some constant R to the D, because it's just the volume of the ball, dr. So you see that if this quantity is infinite, just the origin is almost surely all the time covered. And actually, just a simple argument says that it's everything is yes? Ah, yeah, it's dnu R. Thank you. And you see that if this quantity is infinite, then the process is the occupied set is R2. So if we just have the occupied set, which is just Rd, and if it's finite, then the occupied set is just a non-trivial subset of Rd. So already it's very natural to make this hypothesis to assume this moment on mu. So this was a trivial observation. It was observed by all in 85. So what we are interested in is the phase transition, and it's a phase transition in lambda. So phase transition since I want to maybe keep the notation, I will do many pictures, but hope they are clear. We introduce standardly theta of lambda, which is just the probability that if I look at the connected component of the origin in the occupied set, the connected component is infinite, is unbounded. So then we have a phase transition. We can define lambda c, which is just the sup of all the lambda, so standardly, such that theta of lambda is 0. This is the definition of lambda c. So here theta of lambda is 0, and here theta of lambda is positive. So the picture here, if I'm smaller than lambda c, I just see small clusters. And if I am above lambda c, I have actually an infinite connected component. And with positive probability, I have a path that goes to infinity. And the main question we're interested in is what is the size of the cluster here in this subcritical regime. So first, before going to more advanced question, let's continue a bit like some very natural. And first question is that is lambda c non-trivial? So this was solved by so it's a theorem of Guéret using renormalization argument. Because here you see you have random radii, so standard techniques may need to be slightly adapted. But it was proved in 2008 that if we have this d moment condition, then we have lambda c which is non-trivial. So actually, as soon as the process is non-trivial, I also observe a non-trivial phase transition. So now let's move to the topic, which is sharpness. Okay, 3, sharpness of the phase transition. And let me start by a first theorem that was it's a recent one. So here the dimension is all the time a general dimension larger than 2. So theorem due to Sebastian Zichet in so I think 2016, yes. And he proved the following. He proved that if the radii are bounded, so meaning that if I look at for some, this is 1 for some R0 finite. So I just assume that actually I don't have like all the radii are bounded by some R0. Then for every lambda smaller than lambda c, there exists a constant c such that for every r, the probability in lambda of having a path from 0 to distance r, this decay exponentially fast in r. So this was proved in 16 because it uses a technique from Bernoulli percolation, but it uses a recent proof. It doesn't use the whole proof, but the main tool here is still techniques from Bernoulli percolation, and in particular, it uses some kind of decay inequality. When the size of the balls are bounded, if you look at a long path, you can decompose into 2 paths, and you get some easy decorrelation. And so the proof of this is really using like techniques from Bernoulli percolation, and very in a strong way, the fact that you get some decorrelation when the radii are bounded. So what is interesting for us is the case where the radii get unbounded. So if I look at unbounded radii, there are two obstacles. I mean, there are many other, but I want to give two. The first obstacle, as I said, then if you are unbounded radii, you start to have long-range dependency. If you look at, for example, at the probability that 2 point xy, whatever xy you take, the probability that they are occupied, it's always strictly larger than the probability that x is occupied and y is times the product that y is occupied. Because there is always a positive chance that they are covered by the same ball. And so this makes the techniques, the standard techniques, like really the techniques that work for Bernoulli percolation, very difficult to apply. You don't get this kind of decorrelation. But there is a bigger obstacle. It's actually not true that you have all the time exponential decay. So it's very kind of big obstacle. So when you want to prove something, it's good if it's true. So and actually, I think you see exactly why it's not true. And the reason is that imagine you have big, like the tail is not too small. How would you go to distance n? You just build a big ball. And that costs you maybe sub-exponential. So if I introduce, so let's introduce phi, so what was the notation I wanted to introduce? Yeah, phi r. If I introduce phi r of lambda, which is just the probability of the following event, just there is a very big ball covering the origin. We know that theta, the probability that I have a path from 0 to distance r, it's always larger than this phi r of lambda. And imagine you have polynomial tail of the radii, then this cannot decay exponentially fast, or we make a mistake. So nevertheless, I claim that there is sharpness, and there will be sharpness in a kind of nice sense, is that when you are, what we can say that nevertheless, this is when it's subcritical, and if the tail are fat somehow, you have large tail, this actually governs the one arm event. So this is this will be the content of the theorem, the main theorem. So the theorem, maybe also I want this notation to be clear. So I will not write a very general theorem because the thing is that it becomes technical, but I will just give two cases. So assume the following. Assume that there exists some C0 such that mu of 0 r, mu of r infinity. So I assume that the probability that the tail is exponential. So I assume that the tail of mu is exponential. Then in this case, we have sharpness in the usual sense. For all lambda smaller than lambda c, the probability of having a path from 0 to distance r decays exponentially fast. So I don't put the quantifier, but there exists some c such that for every r I have exponential decay. Okay? So it's quite natural. If I have the sufficiently fat tails, they don't start to play to be together, and I really have exponential decay in the full subcritical regime. But the second case, and we can assume there are other hypotheses, but I will just, for the sake of proof today, I will just make one assumption. If I assume mu of R infinity, let's say, is let's say is 1 over R to the alpha, and we need to make an assumption on alpha which is non-sharp. We need to assume alpha is strictly larger than 5d minus 2. So let's assume that this is exactly, maybe there is constant, but as R tends to infinity, this behaves exactly that 1 over R to the alpha. So we assume exactly polynomial decay. Then for all lambda smaller than lambda c, we have the following. We have that the probability of having a path from 0 to distance r, it's exactly behaving, and it's an equivalent, so it's equal to the probability times 1 plus little of 1 of having just a ball, that this path is realized by one ball. So in this case, it's a sense of sharpness. Just the subcritical model is sharp because just the cluster, if you look here, the big cluster, they will just look like big balls decorated. You don't start to have long chain. So it's actually quite easy to see that you have a constant. To get really equivalent, you really need to kind of do technical, like there is really technicalities here. I will not have the time to explain really how you get the equivalent, but maybe I will explain how we get at least that is the same in the right order. So idea of proof. So the structure of the proof is the following. I have till 20, right? Yeah. So the structure of the proof, so idea. So as I said, we use randomized algorithm, but the thing is that we cannot apply the same technique as for Bernoulli because it would imply exponential decay. And the main step is that we will prove a differential inequality, but it will not be valid for every lambda, but it will be valid only for some family of parameters. So we introduce another critical value, lambda c tilde, which is just the sup of all the lambda such that the probability of the following quantity, lose my red. So having a path from the ball of size r to the boundary of the ball of size 2r, this goes to 0 as r goes to infinity. So this is this clearly increase in lambda, the set of lambda such that this holds. And I just look at the lambda c tilde. So I have 0, and I have lambda c tilde here. And below I have the probability. So let me call this PR because we will use it many times. So this quantity is just the crossing probability from R to 2R. Here the probability, well, I prefer to make pictures anyway. this tends to 0, and here this doesn't tend to 0. So in particular, you have infinitely many scales where it's larger than some constant. And first remark is that it's completely obvious. So remark that we already have this lambda c tilde, which is clearly smaller than lambda c, because if I am supercritical, this does not go to 0, it goes to 1. And so the proof, to do the proof, we do 2 steps. Step 1, and this is where we use the randomized algorithm. If I have some bigger moment condition, so 5d minus 3, d mu is finite, then for all lambda larger than lambda c tilde, and this condition is very important, we have this we have a differential inequality theta prime of r of lambda, so the derivative of lambda is larger than some constant times r divided by the integral of whatever it's not so important the equation, theta s of lambda times theta r of lambda. And so this is where the proof this is where we use a randomized algorithm. And the main difference with percolation is that we have to be above this. We have to have this kind of condition that this does not go to 0. And the reason is that this randomized algorithm gives us some relation between the influence and the variance. And then you have to relate this influence to pivotality. And to relate the influence, they may involve big balls, so you have to do some gluing. And to perform this gluing, you have to kind of use this hypothesis plus this moment condition. So I don't want to go into the details, but this is just exactly the same proof as for Bernoulli percolation at the one, except that we have to do like some kind of technical gluing that says that we can actually prove this equation only above lambda c tilde and under this condition. And a consequence. Yes?
The same as PR of lambda?
Ah, yes, sorry. I forgot to introduce. Thank you very much, François. Theta r of lambda is just the probability to go to distance r. Okay. Yeah, sorry. And a consequence is that we can integrate this equation, and in particular, it shows that as the consequence, it's a trivial computation that shows that actually lambda c equals lambda c tilde. Because this, if you integrate this, it says that either you have exponential decay or you are supercritical, but above lambda c tilde, you cannot have exponential decay, so you are supercritical. Anyway, this is not the part which I want to detail the most. The step 2, and which is actually found it goes back to maybe very old arguments, but I find it very nice. And the step 2 is the step 2 so if I take lambda smaller than lambda c tilde, so here there is no additional condition. We have, so I just do it roughly because I don't want to. The probability under, where is my, I erase the theorem. So if the radii are bounded, then I deduce the fact PR going to 0 implies that theta r of lambda decay exponentially fast. So I don't put the quantifier, but the idea is that if you're above, if you are below lambda c tilde, you know PR goes to 0, and then you actually can bootstrap it to the exponential decay. And if mu of r infinity is equivalent to 1 over r to the alpha, which was my hypothesis, then actually I can deduce the fact I get theta r of lambda is equivalent to phi r. So in some sense, I get some. So this implies that PR goes to 0, and from this hypothesis, the second step, I managed to bootstrap it to something quantitative. And how do you get from something which is just qualitative, this goes to 0, to something quantitative? You just, in general, I mean, if you just think out of a probability of whatever, you know that some function goes to 0, or whatever, you know some, and you just want to get something quantitative. And in general, it's just by, a very nice tool is to use differential equation, because you know that differential equation will tell you, oh, this regime is impossible. And here, the idea is to get some differential equation in R. And this is exactly what a renormalization is. So now I will finish with the last step, and just to give an idea of how we do this second step. So, and what kind of renormalization you do here. So actually, I will explain the following kind of things. We know, let's assume we are at some lambda, we know that PR, so this probability of having a path from R to 2R, goes to 0. How this implies PR something quantitative in R. And this, we use some kind of renormalization inequality. And for people who know percolation, they are very used to this kind of thing. Let me give a first example. So, the first renormalization argument, which is very simple, it's in the case of bounded radius. And actually, let's take a very simple example. I just take constant radius. So every ball is size 1. Then, if PR of lambda tends to 0 as R tends to infinity, this implies that actually there exists some C such that PR is smaller than exponential minus CR. So in the finite case, as soon as I know that this probability goes to 0, actually I know it decays exponentially fast. And this is very easy. This is really a completely straightforward argument. I will just use I will just need a very simple lemma. So lemma, for every k larger than 1, if I look at the probability of having a path from KR and here I take it's of size R. This is smaller than 4 times K, I think, times PR. And this is just a union bound argument. I just cover my annulus with some smaller annulus, and if I have a path like this, I have a... So this is just a technical lemma, and it's completely straightforward. It's followed by union bound. So now let's prove this. If I look at P2R, so the probability, and it's quite easy to see, and this I don't want to go into detail, that's the same as P2R plus 1. So this is what? This is the probability of having a path from 2R, 2R plus 1, and 4R plus 2, whatever. And this I can decompose, so I have this probability. And this I decompose into 3 annuli. I just put some kind of buffer zone of size 1 here. And now I know that the ball, they are all of size 1, so I cannot have a ball that crosses this region. And if I have this path, I need to have this annulus that is crossed and this annulus that is crossed. So just by independence, so this is smaller than the probability 2R plus 1, and here I have just something of size 1, size R, times the probability, the thing they correlate, 3R plus 2, 4R plus 2. And just then by the lemma, this is smaller than some constant PR square. Okay? This is very trivial. If I cross a region of size 2R, I cross 2 regions of size R, and each time I cross a region of size R, I need to pay PR, and the thing they correlate because of this finite radius. So I have directly this inequality. And this is exactly something that, if you have an inequality like this, either I'm uniformly bounded or I decay exponentially fast. And this is exactly, I mean, this kind of renormalization, this is my renormalization, the simplest renormalization inequality. So this proves the first example. And in this case, you see that now you have to take care a little bit more on how things correlate. So I just give another application very quickly, and which hopefully will give you the understanding why how the rest of the proof of the theorem is done. So second argument. So example 2. This time I don't assume a bounded radius, I assume that the integral from R to infinity of s to the d mu is exactly of order R2 minus alpha, which corresponds exactly to this hypothesis that this guy is of the order 1 over R to the alpha. I mean, up to some constant, of course. Then, if I have PR tend to 0, this implies exactly that theta R is smaller than constant phi R of lambda. So we don't get equivalent, but at least we get some constant. And the way we prove it is that we just exactly do this argument, except that this time we need to do like some buffer zone that will vary with, we need to make a bigger buffer zone, like this region that they correlate. It will be, we can take it of order R. So maybe I just write, it's just 2 pictures. So let's look at this time P3R. So, which is just, so let me remind you, that's the probability of having a path from 3R to 6R. This is smaller than or equal to. I divide my annulus into 3. 3 annuli of size R. Then there are two cases. Either the intermediate annulus is covered by a single ball, or I have two paths, one that cross this one and this one, made of disjoint balls. And this one are disjoint. This case, this is easy to compute. This is completely explicit because it's a Poisson point process. So the probability to see a big ball like that is just exactly a constant times r to the minus alpha. Exactly, I mean, it's completely explicit. This is just function of mu. And this time this decorrelates because they are made of disjoint balls. So this is smaller than PR square. So you see you have differential equation this time that P3R is either smaller than this term plus this term. And you see that in this case, this term, if you would add another this term, you would get stretch exponential decay. So in this equation, in this case, when you are polynomial regime, this term kind of vanishes, and this is this one that dominates. So you really have this kind of in general, some kind of duality. Either this is the ball decorrelation term that dominate, or this is the kind of decorrelation term that dominates. If you're in this regime, then this is the big ball that governs the one arm, and if not, it's this one. So maybe I will just add one sentence of conclusion. I said in the middle that I insist that this, I mean, I really used to think that there were just induction relations, but it helped me a lot, and it helped really us a lot to understand, I mean, to see them as differential inequalities. Because when you say it's a differential inequality, you start to think of all the methods that you learned before of differential inequalities. And in particular, to really make things say about that, like you can really start to apply new methods, like methods which are not so natural when you just look at this type of equation, but which are very natural in terms of a differential equation. And yeah, I think it's, I want to, I stop here. Thank you very much. Yeah.
So how robust do you expect this last step to be? Because if you have a generic, like spatial random environment, you don't necessarily have this disjoint ball kind of.
Yeah. So here it's quite nice because the decorrelation corresponds exactly to this, to also the connection in some sense. So for the moment, there is no really robust technique that say, okay, whatever the model you take, the correlation governs. I think this model is quite nice because, like, we really understand how the correlation, where they come from. They really come from these big balls. But in more general models where the correlation are more like, even like if you, like for example, Voronoi, it was the same kind. We understand the correlation, they come from big cells. But when the correlation are more in the definition of the model, it's not clear at all how you do, you have to do case by case for the moment. But I think this decomposition is maybe use a differential inequality to prove something qualitative, and then use a renormalization to get the right kind of estimate is some kind of nice decomposition to go to more general dependent models. Yeah.
In your theorem, there is condition alpha greater than 5d minus 2.
Yeah.
What can you say if it does not hold?
So if it doesn't hold, we can say that we cannot say that lambda c equal lambda c tilde, but we can say that for all the regime below lambda c tilde, we have the sharp estimate because this does not use. But we think it holds, and in particular, maybe I should have had a comment that yeah, to go together with Augusto Teixeira and Daniel Albert, we proved it up to the like in the case in the dimension 2, where you have other techniques that can use. We really went to the bound, to the D dimension condition. So the conjecture is that it should hold here. We don't manage to prove it due to this this technicality that is not really very relevant. So it should really hold till this condition should not be there. Yeah.
So, when you say that basically in the spectrum regime,
Yeah.
No, okay. I mean, in the other result. Anyway, so when you say
the theorem.
The theorem is basically when you say you only have one ball and 1
Yeah.
plus little o of 1.
Yeah.
You expect that the little o 1 is basically have to do with the probability that you have 2 big balls of size. You know that the second order term will be just 2. I mean that you have some sort of expansion of
Yeah, that's a very good question, and I think yes. And actually, in dimension 2 earlier, we were using even this kind of some kind of space length pairs argument using exactly this type of expansion. So yeah, this should be true, and actually this should be doable because the most difficult case here we do. I gave this condition polynomial. Actually, we also managed to get to the equivalent when you have stretch exponential. But as soon as you have like tail which are close to exponential, this becomes more and more tricky. So maybe this expansion should basically work, I think, without problem for polynomial, and then, but then there is all a regime as soon as you get close to exponential where you start to lose a little bit the control.
So if there are no more questions, let's thank Vincent and all the speakers of this first day.